I'm going to talk today about atomic reduction operations, like what they are, why we want them, and how to get them. First, a brief overview about atomic remodify write instruction in LLVM. Atomic remodify write is used to implement high-level software constructs like, for example, the C++ atomic fetch-add operations. It performs a load from a memory location. It then modifies the value loaded using a binary operation like add, and it finally stores the modified value back to memory. And it performs all of these steps atomically. That is, it doesn't allow another concurrent write to modify the memory location in between the load and the store. Many workloads, like, for example, parallel histogram construction, use C++ atomic operations like fetch-add, but discard the value loaded. Atomic remodify write always returns the value that was loaded before the memory was modified. In this example, we have a parallel for loop that generates a bunch of threads, and then every thread loops over an array of integers. And then depending on which atomic bucket an integer falls into, it just increments that bucket by 1. And for this algorithm, the value that was in that bucket before the modification is not really needed. And there are many workloads like this. So today we're going to look at how to optimize atomic remodify write operations for workloads in which the all unmodified value is actually relevant. Multiple LLVM targets have hardware acceleration for this sort of atomic remodify write operations that don't return the old value. And in those targets, those atomic remodify write operations happen to behave like not loads from a point of view of memory ordering in the memory model. When I talk about atomic reduction operations, I'm referring to those types of atomic remodify write operations. And some examples are the store add instruction in the ARM ISA. ARM also has like store min, as well as, for example, the load add instructions, which do load the old value in the destination operand. But when the 0 register is used as a destination, actually they change semantics and become atomic reduction operations. The PTX ISA has an instruction that's called atom that performs a remodify write that loads the old value. And it complements that with a read instruction that doesn't have a destination operand and doesn't load the old value back. When we look at the parallel histogram construction workload, for example, and we compile it to use either the PTX atom instruction that performs a remodify write that loads the old value, or the PTX read instruction that does not, on an H100, we observe a 1.2x end-to-end throughput improvement. So the reason we want these instructions is because they give us better performance in workloads in which the old value is not needed. A fair question to ask is whether LLVM can actually optimize code using atomic remodify write, but that's then dropping the old value into code that uses atomic reduction operations. And while this is sound, in some cases it is not sound to do this unconditionally in general. And I'm not going to go into the details of this program, but this is an example of a program in which, if we actually perform this optimization, we introduce an outcome that's forbidden by the C++ memory model. So in this example program, for example, this optimization is unsound. This optimization has been performed incorrectly in multiple compilers, including GCC and LLVM, and within LLVM, not only in one place like the mid-level IR, but also in multiple backends and in multiple places within the IR. So we have been trying to fix those over time to get correct results. But the problem that we have is that when we do that, we regress certain workloads in which those optimizations are correct. And it's really, really hard to tell apart the programs in which they are correct from the programs in which they aren't. So what are we doing about this? At the C++ committee, we are working on introducing atomic reduction operations as an extension to the C++ memory model, and the C++ atomics and atomic refs in the standard library. So this is essentially new APIs in, for example, the atomic types that perform a remodify write but return void. That is, they don't return the old value. This allows programs to express intent, and it allows implementations like Clang to expose built-ins that then lower to LLVM target-independent intrinsics that then compilers like the backends can cherry-pick to lower to hardware-specific instructions. While it is unsound to optimize an atomic remodify write into an atomic reduction, the other direction is sound. That is, it's safe to compile atomic reduction operations into an atomic remodify write. It just gives you more ordering. One of the techniques that the current implementations are using for integers is that they are implementing some of them using tree reductions. And that happens to be sound for integers because performing the operations in different orders is actually not observable. However, one of the goals that we have is to improve the performance for atomic floating point operations. And one way to do that is to enable those to leverage tree reductions as well. The problem is that in a tree reduction, the operations are performed in a slightly different order in memory. So it is possible to observe that the floating point additions were combined in a different order. So we have extended the specification of this functionality to support these more weaker orderings that allow tree reductions, and they allow optimizations like if you have a single thread performing two atomic reductions back to back, you can actually combine the two values and then issue a single reduction. On hardware like GPUs, this allows, for example, to perform a horizontal reduction across the threads in a warp and then issue a single atomic reduction operation instead of issuing 32 of them to memory. The other limitation that C++ has for atomics today is that they are not safe to use in unsequenced context. For example, when using parallel algorithms, there are multiple parallel execution policies. One of them is called parent-seq, which supports multi-threading and assumes vectorization is safe. And C++ bans essentially the use of atomic in those because atomic operations that load can introduce forward progress issues. These atomic reduction operations do not load, and this is in contrast to the read modify write operations, and that allows us to actually allow them in unsequenced contexts in which we guarantee auto-vectorization. So that means that by giving these operations slightly weaker forward progress guarantees, we can actually increase the amount of, say, C++ programs that people can write in most hardware today. And the good thing is that actually many GPU architectures only support parent-seq, and they do provide atomic operations, but they cannot actually expose them via C++ because the standard forbids it, and this fixes that. So that was it. I've talked about the atomic reduction extensions for C++ atomics. We are going to prepare an RFC to introduce target-independent intrinsics in LLVM, initially compiled to atomic remodified writes, because that's always safe, to at least allow backends to lower those to some of the available instructions. The extension for floating point tree reductions is available, and for the C++ programming language, you're going to be able to use this in the parallel algorithms, in all of them, not only in the parallel execution ones. Yeah. Thanks.
Thank you, Gonzalo.